Hi, I'm Cece and this is Study in Space, my channel dedicated to taking what I'm learning and teaching it to you. This is my first episode, so it's a little rough. I'm still trying to figure out how to put this all together, but in this episode I'm going to talk to you about dimensional analysis. First, we're going to start off by talking about what dimension is. The dimension of any physical quantity expresses its dependence on the base quantities as a product of symbols or powers of symbols representing the base quantities. But what are these base quantities? These are length, mass, time, current, thermodynamic temperature, amount of substance, and luminous intensity, and are represented by the symbols you see here. All measurements can be broken down into combinations of these base quantities, and they obey the rules of algebra. For example, area can be broken down into a length times length. Like in the area of a square, you have side by side. So say you measure it in meters, you have meters times meters, and both of those are units of length. If you take the area of a triangle, you have 1/2 base times height, and base and height are both measured as units of length. So again, you wind up with length times length, or length squared. Either way is proper notation. But wait, you might be asking yourself, what about that 1/2 in base times height? Why didn't we include that? Well, that's because it's dimensionless in this situation, also known as a pure number. And we'll talk a little bit more about dimensionless numbers later. So why does this stuff matter? Where are we going to use this? Well, it helps us solve equations, because equations must be dimensionally consistent. But what does that mean? That means that terms in equations must have the same dimensions. Arguments and functions, like in trig functions or log functions, must be dimensionless, and each side of an equation must have the same dimensions. So let's look at an example. Here we have the first kinematic equation. The final velocity equals the initial velocity plus acceleration times time. Let's look at this in terms of what we measure them in. So velocity is measured in meters per second, acceleration is measured in meters per second squared, and time is measured in seconds. If we take these and think, okay, I have meters. What is meters a unit of? And we break that down for the whole equation, we get length over time equals length over time plus length over time squared times time. If we break that down further, we eliminate the times in the last term. We get length over time equals length over time plus length over time. So is this equation dimensionally consistent? Well, let's look at our criteria. The terms must have the same dimensions. Okay, in the right side of the equation, we're adding length over time plus length over time. That works. That's consistent. We don't have any arguments. We have no trig or log functions or anything like that, so we don't need to worry about that. And is each side of the equation having the same dimensions? Well, length over time and length over time. So this is good. Now let's look at a little bit more complicated an example, Kepler's third law. Kepler's third law states that the period of an orbit squared is equal to 4 pi squared times the radius cubed over the gravitational constant times the mass. The gravitational constant here has a value of 6.67 times 10 to the negative 11th meters cubed over kilograms second squared. So if we break this down into the units it's measured in, we have seconds squared equals meters cubed over kilogram seconds squared times kilograms. Now if we turn that into our base quantities, we have time squared equals length cubed over mass time squared times mass. And if we cancel out the lengths, cancel out the masses, we're left with 1 over time squared, which is just equal to time squared. So our equation doesn't have any terms to be added, doesn't have any arguments, but both sides of the equation wind up with the same dimensions. So this is dimensionally consistent. So I hope this video gave you a brief introduction to dimensional analysis. I hope it made some sense. All my information came either from lecture notes I have from my 101 physics class or from OpenStax University Physics 1 textbook. If you haven't heard of OpenStax, they're an awesome resource. They have quality textbooks for free online. I highly recommend you check them out. I made this video using PowerPoint because I don't know how to use anything else, so that's why it's a little rough, but I'll get the hang of it. Thanks for watching.